Hello AC circuit students. In this lecture we're going to go over a calculation-based method for looking at magnitude and phase relationships for voltage drops over components in a very simple RC circuit with a sinusoidal voltage signal. So we've got, if you take a look at our SMath sheet here, and we'll go over a little bit more throughout on how to use SMath. We've got a TINA circuit simulation clip of our circuit, and we're just using this as a circuit model to show the series configuration. So we have our ground, and then we have a voltage source, and we called it V sinusoidal. So we're remembering that we're imposing a sinusoidal voltage signal as opposed to like a square wave, triangular, sawtooth. And then we have our capacitor and our resistor in series rather than in parallel. And so the goal of our calculations is going to be to determine expressions for the voltage drop over either the capacitor or the resistor. Actually, we're going to do both, such that if we built this circuit on our protoboard, we imposed a sinusoidal voltage signal, say with our picoscope arbitrary waveform generator, and then used our oscilloscope, picoscope or any other, to measure the voltage drop over either component. We could confirm that with our calculations. So we're basically going to build ourselves a calculation-based model. Just as an aside, we could also confirm that model with, of course, with our TINA software. We could simulate it or build it on our protoboard. Either way, our calculation should match reasonably closely what we would measure with a simulator, probably conform more closely to the simulator, but it should be within a reasonable error even with what we measure. So one of the secondary goals of this lecture is to step through an example of how to use the SMath solver sheet. So just a little word about that. What we're seeing here, it looks like just a big piece of graph paper, which is kind of nice. But what this sheet is basically a built-in solver. So it's like a little program, and it's intended to streamline our calculations. So we can type in words, or we can define variables and type in formulas, and the SMath will operate on those formulas using the predefined names of variables that we've designated. So it's a little bit of a cross between a program shell like Python or maybe MATLAB, and a little bit like a spreadsheet. So it's a little bit simpler than either one, but it's great when we want to kind of automate our calculations, where we're doing a lot of complex arithmetic that we need to do to keep track of our phase relationships and that we need to do in AC. So I'm just going to step through this. There's some excellent tutorials on SMath. It is a free MathCAD. That's the type of program this is. It's called MathCAD. It's free, downloadable, and there's great tutorials on it, but I'm just going to basically show you how to apply it for our purposes here in electronics. So we've got the circuit defined. I like to title my SMath spreadsheets with a little title saying, hey, here's what I'm doing with this. So I'm looking for phase relationships and also magnitude for component voltages. So I'm already reminding myself that I'm going to be confirming this with some measurements. So the first thing I'm going to want to do is define input variables. And the way we type in text with SMath is to basically put our cursor wherever we want it on the sheet, and then we can either just start typing and SMath will recognize typically that it's text, or we can do the double quotes, kind of like double apostrophe on the keyboard, and it will bring up a text box. So at this point, SMath is saying, this is just text. We're not defining any variables. We're not putting in a formula. So I'm just going to say input, basically, define input variables. And I like to keep things kind of ordered, maybe in terms of little underlining, keep my sections straightened out, and I can move this text around just by grabbing it and pulling it around. Okay, so now I need to think about my circuit and think, well, what are all the things that I could select about this circuit? Well, I could select the magnitude of my sinusoidal source. So I'll call that V for voltage magnitude. And I'm going to want to use some subscripts to say, well, which voltage? Well, it's the source voltage. And because we're working with AC, of course, we have both a magnitude and a phase. So I'm going to use some kind of repeating indicators of which aspect of an impedance or a voltage or a current that I'm talking about. I'm going to use mag to mean magnitude, and I'm going to use angle to mean phase angle. And in this case, I'm going to use the voltage source as basically the reference phase angle, and then everything will change based on that reference. Now, the way that we indicate a subscript in SMath is to hit the period. And because now I'm defining a variable, not just typing text, I'm going to use a different method of starting my typing, starting my input. I'm going to hit the colon, and you can see that SMath brings up a little equal. So now it's like, oh, we're going to define a variable, or we're going to put in a formula. So that's the double quotes is indicates text, or the colon indicates a formula. Now, as it turns out, if you start typing in text and you never include an equals, or you don't put a colon to tell SMath, hey, this is a formula, it will assume it's text. So if you type in something, then hit an equals, and you haven't already designated as text, quite often SMath will assume it's a variable input, and it'll be very clear when it does that, because it'll bring up the typical colon with the equal, and you'll know, oh, SMath thinks that I wanted it to be a variable. So we know that we now are ready to type in a variable, so I'm going to do capital V period S for source. And you can't type in a dash in a variable name because SMath thinks it's a minus sign, so I'm going to do an underscore mag. So the magnitude of the voltage source. And I'm going to pick something that I would typically start with my picoscope. So I'm going to go 1.00, and now I want to put a unit. And this is one of the greatest things about SMath, is it has an automatic units assignment. It has a library of units. And so I can look up the type of unit that I want to use, and SMath will actually do dimensional analysis with my formulas, and will in fact even alert me if I've made a units problem or units mistakes. That's super valuable. The way I access the units is to use the single quotation or apostrophe, kind of, the shift from what we used when we were designating text. So when I do that, I end up getting a little indicator with a drop down and these little blue symbols that says, hey, what variable would you like? What type of unit? So I'm going to type in a V, and you can see it gives me all kinds of selections, but I want volts. It's very important that you double click on that selection. Don't just type a V and assume it knows it's volts. So you have to actually select it from the library. So I double click, and you can see it's in blue. It says volts. So now I know, okay, it definitely knows what I wanted. So now I'm off to define the angle that's associated with that sinusoidal voltage signal. So because we're in AC, we got a magnitude, we got 1 volt. What's the phase angle? So I'm going to repeat the same procedure. My colon. I'm going to use V for volts, period, underscore S for source, and I'm going to say angle. And my default is to define my source as 0 degrees. So I have basically, it's like defining your ground as 0 volts in DC. I like to define my source as 0 degrees, and then everything will reference to that. 0, and then I'm going to want a unit. So I'm going to look for degrees. So I I typed in a D, and so it's in the D's, and degrees, dimensionless, pi over 180. So that's pretty much that's a degree. So I know I got the unit that I wanted. Okay. So some other things that I'm going to need to define, and this is another aspect of my voltage source for AC. I'm going to want a frequency because I can impose any frequency of my sinusoidal signal. So that's another important characteristic of my voltage source that I'm going to want to add. So same thing, colon, I'm going to call frequency F, and I'll just start with 100 hertz. So, or excuse me, 1,000 hertz. That's usually a good starting point. And again, I'm going to want to I'm going to do the single apostrophe and look for hertz, H. We got all kinds of things. Henrys, hertz, HZ, hertz, frequency, seconds to the -1. That's definitely hertz. Great. So now I've defined everything that I would care about with respect to my voltage source. And now might be a good time to save my SMath sheet. So I'm just going to save it over here. SMath, or how about we go RC, phase, mag, and I'm going to put today's date, which happens to be September 6th, 2022, and I'm going to index it, A, and we're going to keep going there. This is called incremental saving. So as I keep adding more things, I'm going to index that number up. So if anything crashes, if there's a problem, I will have had at least my last version saved. I would very much suggest you do not constantly overwrite your last copy. Save under a new name so that if something happens, you have at least maybe the version prior to the last. You will not have to go back if that's what you need. If you won't have to go back to the beginning. Okay, so what else do we need to define about our circuit? Well, how about the values of the capacitor and the resistor? So again, we'll define those the same way. Colon, we'll go C for capacitor. And let's just put a starting number in of maybe 1 microfarad. So we do micro by saying we have 1 as our significant value times 10, and we use the up caret to denote an exponent, and then -6. And then I do a forward space a couple of times to get to the end of the formula, and I go back to my unit search and I put in an F, and I'm going to look for farads. So there's farad capacitance, farad, there's two different indicators. Well, let's see if SMath thinks they're the same thing. Amp squared seconds to the fourth. These are the actual SI units of farads for capacitance, and we can see they're equivalent, so it's the same unit. So I think an F is easier to carry through my spreadsheet, so I'm going to put that in. And last but not least, I'm going to need a value for my resistance. So call it, actually, let's see if we can show how we can not necessarily need the colon. So I'm just going to type in an R equals, and you can see that once I typed in the equals, SMath realized, oh wait, she's putting in a variable. And I'm going to backtrack a little because from capacitance, I'm going to follow with calculating an impedance, which will be based on frequency. But for resistance, I don't end up having a frequency-based response. So I'm going to go ahead and define a magnitude and angle associated with that resistor, which is not going to change with frequency. So I'm going to define it up here. So I'm going to define R as a magnitude. R, and I did the period to give myself a subscript. Magnitude equals, and we're going to start with, let's go 12 times 10 to the third. So a 12K. And I want ohms, so I'm going to bring up units. ohms resistance. Here we go. As you can see, I'm trying to be pretty careful about lining things up on the spreadsheet, or excuse me, on the SMath sheet. It's not a spreadsheet, it's an SMath calculator sheet, a solver sheet. It's important to keep things in the right order from the top of the page to the bottom of the page because, as it turns out, SMath can only perform a calculation on a variable that was defined further up the page, closer to the top. So that's why variable inputs definitions are always good to put at the top of the page. If you try to put in a formula that references a variable you've defined that it's closer to the bottom of the page than where the formula is sitting, it will say, I can't recognize it, missing variable. So that's probably one of the most important tricks about SMath. Where you put things on the page matters. And this would be analogous to writing a program and defining a variable earlier in your code and then redefining it in a later step. That's effectively what SMath is doing. So I'm going to go ahead and define an R angle. So I'm going to type capital R period, and then I'm going to write angle equals and 0. We know that a pure resistor doesn't have an associated phase angle, or it has a 0 associated phase angle, as opposed to a capacitor, which is negative 90 degrees, and an inductor is positive 90. So the phase angle associated with pure resistance is 0 degrees. So there's 0 degrees. Okay. So the next thing I would need to do in my circuit, and actually, this is another good place for an incremental save. Okay, so the next thing I would do in analyzing my circuit is I would want to take this capacitance, which I really can't do anything with, and turn it into a reactance. So I need an X sub C, and of course it will have a magnitude and an angle, and I might want to express my reactances, my impedances, in both polar, magnitude, angle, and in rectangular coordinates, real, imaginary, depending on whether I want to multiply them or add, subtract them. So I'm going to have another text box where I'm just reminding myself of what I'm doing. So I'm going to calculate total circuit impedance. And make it pretty, underline it to remind myself that this is kind of a header. And you can use all the text you want. If you're working with a teammate and you're trying to give them some explanation of what you were doing, or if you are submitting this to your instructor or maybe your boss, this text allows you to give all kinds of explanation of why you were doing things. I'm lining things up now. As I highlight each one of these input definitions and formulas, it turns blue. And then I come up here, align horizontally, and it will align to the top, not the center. But this just kind of allows me to keep things neat on the page and make the best use of the space. Okay. So next job, let's make an expression for the capacitive reactance, so our X sub C. So this is going to be a formula, and I'm going to use a capital X dot C, and I'm going to start with the magnitude. So magnitude, as we know, is defined by 2 pi. So I can type 2, and now I can come over and find pi, and that is actually going to give me the number. So it's I click on pi over here, and it says, do you want the number pi, 3.14159, etc.? And I go, yes, that is exactly what I wanted, times, now I want to multiply by the frequency and the capacitance. Well, good for me, I already defined those in terms of variables. F, in this case, is my frequency, and I don't necessarily want a unit. I want what I defined. And since I didn't pick the unit, I just picked the letter F. And then I'm going to want to multiply, of course, by my capacitance C. And I don't want the unit there. And of course, I need to raise all of this to the -1. So we know that if I have correctly selected F and C, and SMath is drawing the values that I've defined up here, I should get something in ohms because reactance is in ohms. There's a little bit of a problem. Notice that I used F for frequency. SMath also defines F as a unit, so I may end up needing to pick a different name for that, but it may be okay. So let's see if it will take what I want. Aha! This is a good sign. Notice how SMath automatically calculated my units in ohms. So that indicates that this F and this C are being drawn from further up in the spreadsheet. Now that's an awful lot of decimal places to keep in mind. We can keep them here. We might want to limit that, so we can double click and then right click and say maybe I only want 3 decimal places. And I might want to express this in scientific notation so I automatically have an idea of how it compares to other things. So I can say, I can come down to exponential threshold and say any significant figure beyond 3, keep it at 3, and then use scientific notation for the rest. So let me see if I can get it to do that. Exponential threshold, 3. Okay. So that's it says we've got 3, we're good. Okay, let's, just as a demo, I am going to show you all what would have happened had I tried to draw a variable from that's defined below. So I'm going to take F, which I'm drawing into my X sub C mag, and I'm going to put it below and show what ends up happening. Now, honestly, it should have actually not liked that. Typically it will not want to do that. So I'm going to take a pause and check that out and make sure that this formula is actually drawing from what it needs to. Okay, back from the pause. It appears that in a later version of SMath, it may not be as sensitive to moving variables below the formulas that call on them. That said, I would still recommend that variables that are defined be defined further up the page. I would still continue that practice. Okay, so let's do one last clarification. When we want to define an exponential threshold, we highlight a number, can be the result of a formula calculation. We go down to exponential threshold. The click bar on the 3, the check mark on the 3 means we will only express this in scientific notation if we need a 10 raised to the power of 3 in order to express it. Otherwise, it's going to express as just a regular decimal number. So I'm going to indicate at this point, go ahead and use scientific notation for anything that would involve 10 raised to the power of 2, because I have 100. So now I have my 3 decimal places that we indicated. Decimal places is 3. And I'm now using scientific notation. So that's going to allow me to immediately zoom in and get an idea of what the magnitude of my capacitive reactance is as a function of frequency and capacitance. Okay, so next thing we need to define is the angle of our capacitive reactance, which is really nice. That's pretty easy because that is constant. So we can do another definition. Let's make sure I'm in the right place. So I'm going to use capital X, subscript C. I'm going to use angle instead of magnitude, equals negative 90 degrees. So 90, I'm going to indicate I want a unit. I want degrees, double click, degrees. Okay. So I've already defined the magnitude and angle of my pure resistance up here. And so now I'm ready to go ahead and combine things in series. To to get a total impedance, a Z total for the R plus the C. And actually, maybe I'm not ready to do it because I have my my capacitive reactance in ohms and its angle in degrees, but because I need to add that reactance to pure resistance, or we could call it resistive reactance. It's no reactance, pure resistance. I need to go and express my magnitudes and angles in terms of real and imaginary equivalent components in order to add them. We add reals to reals and imaginary components to imaginary components. So I need to use my trig, although it's very easy trig because I'm operating on a 0 degree and a 90 degree angle to do this. So basically I need to find what is the real component of my resistance, and of course it's all of it. So I can define an R real. So it isn't magnitude or phase, it is simply the real component equals R mag. And I can define a R imaginary, we'll call it imag, equals 0. It's all real resistance. And I'm going to define that as in ohms because I can only add. Let's use the same designation here. SMath being free software, it sometimes is a little fussy with units, so I find it best to always use something that is the same. So I'm going to scroll down. It looks like I'm going to have to go down to the very end for symbols, and it should be equivalent whether I say ohms or I show a symbol. Okay, so I'm going to do the same with my capacitive reactance. So I'm going to define a X sub C real, and that's going to be, again, 0 because capacitive reactance has no real component. It is completely imaginary. So 0 ohms. And X sub C imag is all of it, but I'm going to use a negative symbol to indicate that the imaginary component is negative. And that's what defines that negative 90 degree phase angle. So it's going to be negative times the entire magnitude. So no need to take a sign. Actually, I'm taking the sine of negative 90 degrees and then multiplying by the full magnitude. And in this case, when I defined the R real, what I did was I took the cosine of 0 degrees and multiplied by R mag. And of course, I got the full thing. So I'm going to do basically simplify it. I'm going to leave out the trig here and just say it's negative X sub C mag. Okay, so it's a little bit repetitious, but I'm kind of reinforcing that I'm going between a polar expression here, and now I have a rectangular expression. So how do I get a total component in terms of using my rectangular? I add reals to reals and I add imaginaries to imaginaries. So I can now define the total impedance of my circuit, Z, and I'm going to start with a Z real. I could say Z total, but there's only one Z, so I'll just say Z real equals R real plus X sub C real, and surprise surprise, that ends up being my 1200 ohms, and Z imag equals R imag. So now I'm matching the exact syntax of the variables that I defined prior, so I'm not going to add that to my X sub C imag. Okay, so now I've got a negative. Okay, so now if I want the total magnitude, so Z mag, I'm going to use my Pythagorean theorem, and I'm going to say that's going to be Z real squared plus Z imag squared. Scroll over, raise the whole thing to the 1/2, and I should get something in ohms. And oh boy, that's only a little bit more than my total real component. So what this is saying is that the magnitude of my imaginary component, the contribution of the capacitor, is tiny compared to that of the resistor, which you know, is probably a function of the fact that we have, you know, different values. But that's the first thing we want to check when we get to these intermediate numbers is, do they make sense given what we have, and how would they change if we change something else? So given that this value is dominated by the resistance, I would expect to see a total Z angle that's close to a pure resistor. So let's see what that ends up being. So I'm going to go ahead and calculate a Z angle, so the angle associated with my total circuit impedance. And, oops, S-math is being fussy. So for that, I'm going to use the inverse tangent, A tan, of my Z imaginary, Z imag divided by my Z real. So now I'm using some trig, equals. Now this value is in radians. That's S-math's default. And I want this in degrees. So I'm going to indicate, hey, I want to change units. It gets rid of the number that I calculated. I select degrees, and it should give me the equivalent value in degrees. And if it doesn't, we're going to try again. Again, this sometimes a little bit fussy. See, now it thinks that I'm trying to define a new variable. Well, I may have to take a pause and wrangle with it there a bit. Okay, so negative 0.7599. Okay, that is actually something that would make sense when we put together with the fact that we have a very, very tiny contribution from our capacitive reactance and our magnitude of our total impedance. So we're on the capacitive side. We have a negative impedance angle. If we had an inductor, we would have a positive number. So that's as expected, and that's because our Z imaginary is negative. So A tan of a negative value is going to be down in that lower quadrant. But it's less than 1 degree. So it's almost pure resistive. If we want to do a super quick check on this, just to make sure we haven't gotten a sign wrong or something, one thing that we could do at this point is to go up into our frequency and say, let's go with a really low frequency that's almost DC. That would make our capacitive reactance very high compared to our resistor, and we should see that reflected in our XC mag, in our Z mag value, and in our phase angle. So let's knock off a couple of orders of magnitude off of our frequency, hit enter, and S-math recalculates for us. Here's the big strength of doing this as opposed to a sheet calculation. So let's see what happened to our magnitude of our capacitive reactance. We went from 10 to the second to 10 to the fourth. So it was a 2 order of magnitude change, which makes sense because our frequency is in the denominator, so it's kind of linear change. And let's look at our Z magnitude. Now we're basically, we have 19,000. So 12,000 of that is coming from the resistor. The rest is coming from the capacitive reactance. And our phase angle has pulled from less than 1 degree negative to negative 52. So that is going in the right direction. That's a good confirmation that we haven't made a calculation boo-boo or an entry. So we're going to put that back to our 1 kilohertz. And this is another excellent time to go ahead and save, do an incremental save. So we're up to version C. I'm going to take a quick pause, and then we're going to go ahead and apply Ohm's law to our voltage source and our total circuit impedance to get an expression for our circuit current. Then we'll go ahead and take that current and we'll apply that to the individual reactances, or we can call them individual impedances of each component, and find the voltage drop over each one of those, which is what we would then correlate to our measurements. Okay, we are back after a pause, and we are ready to use our expressions for total circuit impedance, our Z. We've got a Z real, Z imaginary, and what we're going to use to calculate circuit current is that same impedance expressed in terms of magnitude angle. That's what we use to multiply and divide, which is what we need to apply Ohm's law. So we'll give ourselves another little header. Calculate circuit current. We could say total circuit current, but it's a series circuit, so there's one current. So keep it simple there. And in order to do this, we're going to, of course, apply Ohm's law. So we can define current using our same kind of scheme. I'm going to define a current magnitude, so I subscript mag, and I'm going to calculate that by basically dividing V source by the magnitude of the total impedance. And I've already defined those, so all I have to do is call in the variables. So I'm going to call in my VS mag. I'm going to divide that by my Z mag. And I should get something in amps. So that's a good sign. So again, SMath immediately gives me my variables, units of my variables if I've defined them. So that's a good indicator that I got that right. So now I need to know what angle that current is, because again, we're in AC. Everything has kind of two components. We've either got a real and imaginary component, or its equivalent, a magnitude and a phase angle versus our reference. And our reference is 0, which is our voltage source. So I'm going to define the angle part. So I'm going to call it I angle. And in order to divide basically polar notation expression, of course, we subtract the numbers. So I'm going to subtract my VS angle. I'm going to subtract my R angle from my VS angle. So I have VS angle minus Z angle. So that's the way I divide polar numbers, is I end up subtracting them. And I'm getting a 0.133. This is in radians, so that's an angle in radians again. So I have to do my little notation that says, hey, I want this in degrees. So again, we're seeing that same number. So notice my impedance, my total impedance was negative, indicating it was net capacitive, but the current's positive, and that is because of the operation of Ohm's law, where I'm basically dividing my zero angle voltage source. Again, that was arbitrarily defined as 0, but I'm subtracting my my total impedance because I'm dividing it. So this is all, even though we're seeing a subtraction, this is all part of calculating applying Ohm's law and calculating my polar relationships. I divide the magnitude and I subtract the angle. So now effectively I have 8.3326 times 10 to the minus 5, or about 83 microamps at about 0.8 degrees. That's my current, and that's flowing through everything. So now I can reapply Ohm's law to get the voltage drop over each component. So I have this current, angle and magnitude, going through each component. So if I want to get the voltage drop over each component, all I have to do is multiply current times per component impedance. So we could call it Z, or we can go back to our, in this case, it's very simple, the impedance, quote unquote, of my resistor. And it is legitimate to use the term impedance to suggest, to indicate either a pure resistance, a capacitive or inductive reactance, or a blend. So impedance kind of is a good term to use if you're really not sure what it is, or if you want a grab bag to just say something that resists current flow, whether it's by storing energy in a capacitor, in an electric field, storing energy in a magnetic field in an inductor, or just turning it into heat in a resistor. It impedes current flow. That's why it's called impedance. So we could denote our pure resistance as our resistive impedance if we want. So we're going to give ourselves another little a little heading. So we're going to say we're going to calculate the voltage drop. We're going to do the capacitor first. Voltage drop over capacitor. So we're partway there in calculating what we want. So this is actually going to be, now we're getting into something, what we're calculating now, the voltage drop over a capacitor, is something that we can actually relate to a measurement. So we're now getting into the exciting stuff that we can correlate to a physical measurement. So I'm going to define a new variable, the voltage drop over my capacitor. It's going to have two parts, of course. It's going to have a magnitude and an angle, and I could also call it a real and an imaginary component, but I'm going to start with magnitude angle because that's what Ohm's law is going to give me first. So I'm going to call it V sub C for voltage drop over the capacitor, whoops, underscore mag. So I'm going to go for the magnitude first. So using my polar arithmetic rules, I'm going to apply Ohm's law to the magnitude first, and I'm going to say V sub C mag is going to be equal to my X sub C mag times the current flowing through it, which is I mag. And lo and behold, I get a number in volts, which is a good sign. Now I'm going to look at the angle of that voltage drop. Of course, everything has a magnitude and an angle, so V sub C angle. I like to use some consistent notation so I don't confuse myself. And so remember, this time, since I'm working with angles, I add. I'm multiplying them, I add the angles. I multiplied the magnitudes, I add the angles. That's my rules of polar arithmetic. So I'm going to have X sub C angle plus I angle. And I get another dimensionless value, which again automatically pops up in radians. So I say, give it to me in degrees. So let's see, does this seem reasonable? Here's another chance to look at something reasonable. I've set my frequency back to 1,000 hertz. So most of the current is being impeded by the resistor. So basically, I have something that's going to be at one extreme, and the voltage drop over my capacitor should be, pretty much mostly a function of the capacitance, the capacitive reactance. So that does make some amount of sense. I'm going to double check all of this later on. And as a word of warning, it is for some people it is very non-intuitive to keep track of the net phase character of the current or a voltage drop. And remember, we do go back and forth as we apply Ohm's law, and it's opposite quite often, because Ohm's law quite often is expressed as a quotient. So not to worry, we'll go ahead and check these, but it is a negative number, which is important. If we had a positive number, that would have indicated we had a sign error somewhere. So we're going to go ahead and do the same thing for the resistor. We're going to look at the voltage drop over the resistor. We're going to do the same thing. Voltage drop over resistor. And before we get too excited adding more formulas, we're going to do an incremental save because we're pretty happy with our calculations so far. And if SMath crashes, we don't want to lose it. So, okay, so we're gonna invoke Ohm's law again. So we're going to look at the voltage drop over our resistor. We're going to start with the magnitude, and that is again just Ohm's law. So what is the magnitude of our resistor? R mag times I mag. And wow, not surprising, with 100 hertz giving us a very low capacitive reactance, that resistor is dropping almost our entire 1 volt. So it is providing the bulk of the total impedance, which we're not surprised about because that's correlating very well with this number. So let's do the same with angle. The voltage, the angle of the voltage drop over the resistor equals, so again, we're gonna do a sum that correlates with that product for Ohm's law using our rules of polar math. So we're going to use our angle plus, it's not a quotient, it's a product, so it's going to be plus I angle. And we have a positive number, which we're going to, again, of course, SMath wants to give it to us in radians, so we say, nope, give me that number in degrees. And we have, again, this shouldn't be surprising, we have our less than 1 degree, but it's positive. So let's look back up here. Our total impedance was negative, and now we have something positive. So, and it shouldn't be a surprise that these two numbers are the same but a different sign. That is an artifact or a function of the fact that our angle is 0. Remember that our phase, our voltage drop over our resistor is going to basically be in lockstep with the angle of the current. And in fact, look, 0.755, 0.755, because the impedance of our resistor is at a 0 angle, our R angle for pure resistance is always going to be 0. So the angle of the voltage drop over the resistor is the same as the angle of the current. And that's how we can use a pure resistor, voltage drop over the pure resistor, to actually measure the angle of our current. We're going to use this very relationship. So kind of like using a shunt resistor to get the magnitude of a current, we can use this 0 phase angle relationship of the impedance of pure resistance as a great way to get at what is my current doing when I can only measure voltage. No problem. We get that 0 degree phase angle. Okay, at this point, we can do another incremental save, because if we trusted ourselves to not have made any mistakes, we would be all ready to compare values to something that we got from our measurement. We could go ahead and we could measure the total circuit voltage with our oscilloscope. So we could basically take, impose our signal on our series RC circuit, and then we could measure between this point, and then display it and mathematically manipulate it versus a measurement taken at point A here. So basically point B versus ground, point A versus ground. We could get basically magnitude and angle of V sub R and V sub C, either directly or by difference, depending on which way we had arranged the circuit. It is always a good idea, though, to take advantage of natural checks. And one thing that we can do to check ourselves to make sure we haven't made a boo-boo is to apply Kirchhoff's voltage law using our magnitudes and angles of the voltage drops over our components and see if we can add them up using Kirchhoff's voltage law and get the source voltage, because we know that basically whatever voltage we drop over the capacitor and the resistor put together should equal what we put in with the source, because we start at ground, 0 volts at our some reference angle, and we raise the voltage, we add energy with a particular magnitude and phase with our voltage source, and then we take that away with capacitive reactance and resistive dissipation, and we should come back to where we started. So the combination of the voltage drops over the capacitor and the resistor should equal the voltage rise that we imposed with the source. Let's see if that's true. And if we can show that that's true, we can move forward with confidence, and we can use this spreadsheet, or excuse me, this calculation sheet, our SMath sheet, as a way to check ourselves when we go ahead and make our measurements, making sure we've maybe put our oscilloscope probe in the right place on our circuit. So we're going to indicate we're doing this. So we're going to say KVL check for magnitude, and that's a little bit easier because we don't have to do as much wrangling back and forth with real imaginary Cartesian expression versus angle magnitude polar. Okay, so KVL check for magnitude. So this is pretty easy. We can use Pythagorean theorem to go ahead and combine basically VC mag and VR mag. So we know that these are literally 90 degrees apart. So we're going to use the properties of a right triangle to say the total mag. We can use those right triangle Pythagorean properties to say, okay, I'm looking for a hypotenuse. My V total mag is the hypotenuse of a triangle whose two legs are VR mag and VC mag. So Pythagorean theorem says I take the square root of the sum of the squares. Ooh, not the quotient. So I want VR mag squared plus VC mag squared, raise the whole thing to the 1/2, which is the same as taking the square root in this case. Aha! Good sign! I get 1 volt, which is exactly what I was hoping to get. That's our source. And in fact, I can even show that this would hold true if I had a 2 volt source. 2. So that's a good sign. Okay, so that's my first check. I've shown that the magnitudes of the voltage drops over the two components is going to add up to the magnitude of the source. So the next thing I want to do is make sure that the phase angles of the voltage drops over the components add up to the phase angle of the source. So for that, I need to do a little bit more complicated math. I can't just add the angles straight up per se. What I need to do now is re-express the voltage drops over the capacitor and the resistor in Cartesian components, and then basically use those with my trig relationship. I have the total magnitude that I got with Pythagorean, but I need effectively those legs of the triangle in real and imaginary components to apply my inverse tangent to get the angle between them. So I know how big the legs are, but I need to I'll need to get those real and imaginary components. So I'm going to take a quick pause and then start up again. Okay, back from a quick pause. So we're going to go through the KVL check for angle. Now, as it turns out, because the voltage drop over my capacitor and my resistor are for this particular frequency are so far apart, it's not going to necessarily look like I needed to go through and calculate real and imaginary components and do the full tally, but it would be necessary in cases where we have a current that is closer to something in between 0 and positive or negative 90. So what I did in this case to get my second sheet is I took my text box and I moved it down into this shaded area, and the math CAD, the SMath said, aha, you probably need another piece of calculator paper. And in fact, it just did it again. No, I don't need 3. I don't know where it went this time. You can still do the Control Z and back out of something you didn't want to do. Okay, so at this point what we're going to want to do is swap and get re-express our component voltage drops instead of magnitude angle. We're going to want real imaginary. So I'm going to start with V sub C real. Now I get to use my trig. So that's going to be V sub C magnitude times cosine of my V sub C angle. So that should be something a little bit less. And V sub C imaginary. Now notice this is not the same as what we would have for a pure resistive or capacitive situation, because the current is a blend, and that's what's giving the voltage drop over a capacitor. Even though it's a capacitor, its voltage drop is reflecting the fact that the current angle is being influenced by the resistor. So that's why it's always best to just go through the rules and add things up component by component. So the imaginary component of the voltage drop over our capacitor is going to be the VC mag times sine of our angle. Typing and calculating and talking at the same time. Okay, so real and imaginary components. Do a little quick head check. Now I'm going to do the same for my resistor. So VR real equals VR mag times cosine of VR angle, and I'm calling in terms I've already defined. So this is making some amount of sense. So the voltage drop over the resistor is mostly real, because again of our high frequency, that's reflecting most of the drop in the circuit. But it does have a component of imaginary because the current does. So we're going to say VR imaginary equals VR mag. See, I'm applying my trig, sine and cosine times sine of the subscript r angle. I'm going to take the sine of an angle, and I'm going to get another amount in. So I'm going to do a quick check, see if that makes sense. Okay, so now I'm going to add reals to reals and imaginaries to imaginaries. So I can say V total real equals VC real plus VR real. Well, that's reassuring because I had a 0 phase angle on my source, so I better not have any imaginary. In fact, we've already got a good sign. These two are looking the same. They should cancel out. V total imaginary equals VC imaginary plus VR imaginary. Okay, so SMath carries a whole bunch of extra decimal places it doesn't show. So it's saying you got a little imaginary component, but we're going to say that 10 to the minus 16 might as well be 0. So what we've shown at this point is that the phase angle, we're going to do a final expression for it. But remember, when we defined our voltage source, we said we defined a magnitude of 1 volt, and we said it's going to have a 0 arbitrarily. We're going to have a 0-degree phase angle. And then we use that number all the way through our calculations. So a 0-degree phase angle, if we were to apply our trig to express this in terms of real and imaginary, we could say that our source magnitude was 1 volt real, 0 volts imaginary. So the fact that we're getting 1 volt real and 0 volts within calculation error imaginary for our circuit says that our KVL check for angle is giving us what we hope to see. So the sum of the angles associated with the voltage drops over the components is summing to what we imposed with the source, which is KVL for angles here. So we're going to go ahead and just top that off with a V angle expression. So we can just say V total angle equals, and we'll use our A tan of V total imaginary divided by V total real equals, and I'm going to put that in degrees. So again, something still pretty small. So let's just for giggles, let's reduce the frequency again down to 10 hertz, and we should see this change to something that is not close to 0. Actually, we ended up with something going the other way, the total angle going negative. So still, excuse me, I misspoke. This is our check, so it should still be close to 0, but this time the calculation error swung to the negative side, so that is actually still a good check. It should always be about the same as this. If we wanted to make this change, this should always be, the total angle should always be by KVL, whatever our source angle was. So if we changed our source angle, we should see that reflected here. I'll go ahead and try that. I haven't tried that before, so this will, you're the first. So 30 degrees. So we're seeing that's a good check. So basically we just confirmed KVL for angles. So if we used a 30-degree source convention, we saw that our voltage drops, angles of our voltage drops over our components confirm that. So this is a great time to do another incremental save. So we now have a calculation aid that we can go ahead and build this circuit. We can hook it up to our waveform generator and our USB oscilloscope, or whatever oscilloscope you happen to be using, and we can change our source input, use whatever expression we want for the source angle. I find it easiest to use 0. We can change the frequency to whatever frequency we impose, and then we can adjust our capacitor and our resistor to the values of the actual components we use. And then at that point, having done that, we should be able to check our voltage drop over our capacitor in terms of magnitude and angle that we measure on our scope display with what we've calculated. So we have an instant check of what we should see, including, based on this negative sign, whether we are lagging or leading our total circuit expression, which should be whatever we're imposing with our source by KVL, given that this is a series circuit here. So we are done. This was a very long lecture. Apologies for the hour and almost 15 minutes. But main takeaways, little tutorial in SMath, how to go ahead and manipulate that. Good power of having a MathCAD expression as opposed to hand calcs. You can change things so you have an automatic aid to check your either your simulation values or your as measured values when you start building a circuit. And kind of a small review of our polar value mathematics, switching between rectangular and polar expressions when we need to either multiply, divide to apply Ohm's law, or add and subtract to combine voltages or impedances for our components in series. I'll add a note that we didn't include any parallel configurations. Those would have followed the same exact approach, except our total impedance expression would have been more complicated because we would have used our parallel combination, and we would have had to gone back and forth between our polar and our rectangular math, so using our trig back and forth, and then when we reapplied Ohm's law, we would do it obviously for same voltage drop, different currents. So we would have a different current, the different magnitude and a different angle going through each of our two components. But other than that, we would have followed the same procedure. Define our input variables, calculate our total circuit impedance, get an expression for our total current, and then either calculate our voltage drop over each component or our current through each component, and then use KVL or Kirchhoff's current law, or both, to do our check. So thanks, and stay tuned for videos showing the circuit build and picoscope demo for this same circuit, different component values, and also a simulation. So stay tuned.